Okay, so welcome everybody. This is day 2 of the Dask Down Under workshop at the Dask Summit. Our next talk is going to be called Characterizing Vegetation Patch Proximity and Size Across Australia with scikit-image and Dask Map Overlap. It's presented by Ben Leighton and Kimberley Opie. Ben Leighton is a data engineer and generalist with diverse experience across environmental informatics and scientific computing. Recently, he's been using Dask, Python, and the ESI data science platform, Easy, to process large amounts of identify landscape. Oh, sorry, I beg your pardon. To process large amounts of data and identify landscape change in satellite imagery. He mixes image processing algorithms with Dask to figure out vegetation shape and proximity to help understand the behavior. Kim is a member of the bushfire adaptation team at the CSIRO Land and Water Department and is using Dask in bushfire behaviour modelling. With over 15 years experience as a data scientist, Kim specialises in development of software solutions, particularly for large volumes of spatial data, acquisition and analysis of remotely sensed data, geographic information systems, data management and spatial analysis. So it sounds like it's going to be a great talk. Take it away.
Thanks very much for the introduction, Genevieve. So yes, it's characterizing vegetation patch proximity and size across Australia with scikit-image and Dask map overlap. I think that got cut off in the, so it's map overlap at the end there in the schedule. And Kim and I are going to be presenting. So I'm about to hand over to Kim, but first to set a very high level context. So the story that we want to tell today is about how we're analysing shapes and proximity of landscape features to help model fire more accurately and at a fine resolution across fairly massive data sets using image processing libraries in parallel with Dask. So we're going to run through a bunch of different stuff. We're setting some context now and we'll continue to do that. And then we'll talk about vegetation proximity and size, looking first of all at a result, like what the end product is, thinking about why it's important to understand vegetation size and proximity for fire behaviour, understanding the nature of the problem. So why is it a tricky problem to solve computationally? And talking about the building blocks of a solution, then detailing a little bit more about the solution. So how we used Dask map overlap and tiling, and actually hopefully give a bit of an introduction for those who haven't ever used map overlap, a little bit of an introduction on how map overlap actually works and some visualization on that. And a concise overview of the full algorithm. Probably won't go into too much detail there unless people have questions, and some potential future for this work and challenges as well. Now I'll hand over to Kim.
Thanks for having me as a speaker at the Dask Down Under. I think my work's interesting and hopefully you find it interesting as well.
Yes.
Yeah, all right.
Okay.
Sorry, Ben's mouse.
Yeah, sorry, I've got an ergonomic mouse. It's a problem.
So a bit of an overview of why this work was actually undertaken. Bushfires are a natural part of the landscape in Australia, and it's pretty essential ecologically. But bushfires do pose a hazard. So they're a hazard when they interact with assets or threaten human life. We've thankfully got some science and experimental fires behind being able to develop bushfire behaviour models. A lot of evidence lets us know that fire line intensity is a good value to measure that hazard or potential hazard, and it incorporates basically the essential elements, the weather, the terrain, and the fuel characteristics. So the problem that our client approached us with was to assess bushfire hazard across Australia for the critical telecommunications infrastructure. The things that we need to consider when we're doing that is that it's a long-term projection. So we're using the inputs for the bushfire behaviour models into the future for the life cycle of that infrastructure, say on a 50-year horizon. To cover Australia, we have reliable data set discretely for states and territories and Australia-wide, and they vary in resolution and quality and attributes. So we kind of had to paste those all together. And yeah, one thing that we need to also consider, and this is probably the crux of it, is that bushfire behaviour models give us a potential fire line intensity. So when we're modelling that for smaller patches and corridors of vegetation, it's very important to reduce that intensity. How do we figure that out? This is a very nice graph. It shows the relationship between the rate of spread. For those that are unfamiliar with bushfire behaviour models, rate of spread combined with fuel load results in the fire line intensity. But I won't go too much into detail about bushfire behaviour modelling. So this is for a variety of wind speeds in grass fire, and we can see that there's a decline in the head fire width and therefore the rate of spread for smaller patches of corridor, smaller patches with that have a constrained head fire width. I hope I've explained that properly. Yeah. So the landscape is a patchwork of what we call continuous vegetation and discontinuous vegetation. So continuous vegetation is a patch of vegetation that can sustain fire running through it without unimpeded, basically. So we've got this very patchwork landscape where we need to modify the rate of spread, and that's not only the size, but the distance from other adjacent patches of vegetation. Yeah, so, I think that's it.
Okay, great, thanks.
Let me know if you've got any questions.
Yep, we can take them now or at the end. If anybody's got a burning question, we can probably ask it now, but otherwise we can keep going. So thanks, Kim. So we have this is an image which shows a small fraction of continuous vegetation. So effectively, prior to processing, this was like a binary image showing vegetation. And what we end up with after we go through this entire process is we end up with a modified version of this vegetation continuity layer. And you can see here that small isolated patches of vegetation have been identified, and we've assigned them with a rate of spread modifier. And we haven't detailed the exact rules in this presentation because they're fairly complex about the different rate of spread modifications that happen. But you can see there that the green patches actually have less rate of spread modification, I believe, because they are slightly larger typically than the yellow patches. But the rate of spread modification also depends upon the distance of the patches from other patches and whether they can sustain a full fire. So size is important because, as Kim said, if you have a large enough amount of vegetation, then the fire will reach full intensity. Otherwise, it will be constrained in its intensity. And also proximity matters, because if a patch is very close, it's very small, but it's very close to a large patch of vegetation, then the neighbouring fire will influence the intensity of that fire and allow it to get to full intensity. So as far as I'm aware, this is not an embarrassingly parallel problem, because you need to take into account neighbour pixels to look at vegetation patch size. So if you consider the kind of two patches on the right there, you need to know about the connectivity of all of the pixels. And I think in Draga's presentation yesterday, the label image function was mentioned quite a lot, and we also use that here to find the connectivity of a patch. Once we understand what neighbour pixels are connected, we can just add them all up and determine the size of the patch. And so proximity also is not parallel as far as I'm aware. So we use the, it depends on the distance between patches. And so we need to understand neighbour information again to be able to process and get an answer there. So we wanted to use standard image processing algorithms for this, if possible, because they're robust and well tested. And apply, if possible, because we're still processing quite a large landscape, we wanted to be able to use image processing to parallelize some of this with Dask. In the future, we'll probably use Dask image. Initially, I had some issues with labeling performance, and possibly there could have been a bunch of reasons for that, including the way I was using it rather than any fundamental issue with Dask image, but we'll talk about that more when we get to future work. So the building blocks, so by the way, we're dealing with about, overall we're dealing with varying amounts of data and varying resolutions, but it's about 300,000 by about 20,000 pixels. So it's in the kind of gigapixel range. These are the building blocks of our building blocks for solving these problems. We used dilation as a metric to find distance. There are some distortions that you can see there on the right when you do that, but it does give us an estimate of the distance between patches. We used labeling, which I mentioned before, so labeling algorithms, which are readily available in scikit-image and other image processing libraries to find connected areas of the image. We used quite a bit of patch grouping and ungrouping. So using conditional statements with NumPy and Dask to actually merge patches and then find out we know then that those two patches are proximate to one another because they touch, and they'll look like a contiguous patch now when we label them. And then we actually will use grouping and ungrouping and effectively where conditionals to find out what original patches intersect with that new merged patch to go back to the original patch information to identify patches that touch. So just a quick refresher, most people here I think are probably pretty familiar with chunking being a key to speeding up processing with Xarray and Dask. So this is a different data set, also another fire data set where we can see the visualization in Jupyter. You can see that data structure there, the three-dimensional data structure, which is the small dimensions are space and time, and the long dimension, a space, and the long dimension there is time. And you can see it's being divided up into lots of little chunks, which is great because if you're doing independent processing on pixels, then you can process those all independently and distribute them out. So it's an embarrassingly parallel problem. So Dask is fantastic for this. It improves speed and allows lots of memory to be utilized. So we wanted to do that, but we can't just, because I've already described why we can't just go and split all of the pixels independently and process them all independently. Dask provides the ability to tile. So we can use something like Dask map blocks to go and distribute this image in parallel. But we're going to find that actually doesn't give us the right answer. And here's some visualizations of what chunking actually looks like applied to an image. So this is a binary image effectively, where you can imagine that circle is a patch of vegetation. And the bottom image is a visualization of what happens when we chunk that image and we actually identify all of the chunks. So the color scheme's a little bit strange there, but there are actually 4 chunks there, and each quadrant of the circle is in a chunk when we chunk that image, which is 200 by 200 into chunks of 100 and 100. So if we calculate the area of that circle with and without map overlap, using the label function, we can see that we're going to get some pretty interesting and strange answers. So with map blocks, there are 4 unique count results, 1 for each chunk and quadrant. So 2 of them are the same, which is why we've only got 3 answers here. But it doesn't really give us an answer where we can look at any pixel here and understand what its area is, what patch area it belongs to. But really what we'd like in our case is to have every pixel in a contiguous patch assigned with the area of that patch. With map overlap though, and appropriate parameters, we can use neighbour information to build a complete area of the object, even though the boundaries of the object span across the chunk boundaries. So under the hood, what's map overlap actually doing? So map overlap tiles, just like map blocks does, but it includes a buffer or boundary from neighbouring tiles. And then later the boundary will get automatically trimmed off. So effectively, map overlap can help remove edge effects when doing various kinds of processing, including this kind of processing. So you can pass a parameter. Normally, we would actually pass that parameter called, we would not pass the parameter. We would use the default and allow trimming to take place. And if you set that to false, though, you can actually kind of visualize what's happening, which I found to be pretty interesting. So this is actually just the same image that we started with on the previous slide. So it's just a circle in the middle. The original data set is just a circle in the middle of a NumPy array, basically. And the original dimensions were 200 by 200. And here what's happened is we've actually run map overlap with a buffer of 50. And you can see that and visualize effectively what each processing chunk looks like now. And you can see that each chunk, each quadrant, if you like, now has the full circle information available in it. And so when you run independently in each of these chunks, a label operation and then count the number of pixels in the contiguous area, you'll get the same answer in each quadrant. So effectively, this is the answer you get now, which is the correct answer for the area of this circle. And this is actually still chunked into 4 chunks. So there are 4 independent chunks now, but because during the map overlap operation, enough information was sourced from the neighboring chunks, the complete feature was available to be processed by the image processing algorithm, which is what we needed in our case. So one of the things that was nice about our problem, this doesn't solve all problems. There are still potentially edge effects, right? Because you've got to consider that there could be very large features which actually span across the boundaries of that map overlap, the buffer that map overlap provides. In our case, as we were talking about earlier, we are only interested in small features. So this is really good for this problem because we can guarantee basically that we have buffers large enough to consider the longest possible small features. And here's a visualization of that where the top visualization shows what would happen if you had a linear feature, which was kind of around our maximum area threshold. And it was very close. So it just started in one chunk and it spanned that chunk and into another chunk. So that would be our worst case scenario that we'd want to consider. We wouldn't want any information there to be lost. So we would need a buffer large enough to consider that worst case scenario. So it's kind of good to think about worst case scenarios in figuring out how to solve your problem, edge cases, if you like. And this is the kind of edge case or kind of case of interest at the edge of our problem space that we were kind of looking at. We also actually used some online tools. So we used a tool called Piskel, I think, which is actually a GIF tool. So it's a pixel painting tool. And Kim and I used that a bit to actually paint pixels and then discuss whether or not our algorithm was going to work properly in that case. So we found that quite a useful tool as well. Most of this kind of visualization we just did for this presentation. So it was that pixel tool that really gave us some kind of concrete understanding of special cases in our algorithm. So this is the kind of full algorithm or a simplification of the full algorithm. And this is kind of work that Kim pioneered in using ArcGIS. And then we kind of took and implemented in an image processing pipeline in Python. So that allows us to scale beyond Arc and remove some of the licensing issues with using tools like Arc. And it really gives us that full flexibility that having Python, pure Python, if you like, or unencumbered Python gives us. So basically what we do is we start with a continuity binary, which is the image that some of the images that we showed and talked about earlier, and a rate of spread reduction, which is initially just 1, effectively, so there's no rate of spread reduction. We actually upsample the images, and the reason we do that is because during dilation, if we don't upsize, there's a certain number of dilation iterations helps us determine the distance between patches. But say naturally 2 features are 5 pixels apart, but we actually need to measure a distance that's exactly half of those 5 pixels. We can't actually do that because we can't divide a pixel in half during the dilation operation. So what we do is just double the resolution of everything so that we guarantee that there's always, that we're going to get an even number of pixels between different patches. So we get patch size, we store large patches and small patches, except excluded large patches, which I'll get to later. We kind of then go through a parallel workflow of iteratively dilating large patches. Sometimes we'll iteratively dilate a single, two patches, half the distance that we're interested in, or sometimes we'll iteratively dilate a large patch, the full distance that we're interested in. We'll label the merged patches in both cases, and then we'll recover the original patches from the merged areas to actually find out what original patches in vegetation touched. We'll check to see that the patches, in the case of large patches, are within the size range that we're interested in. And if so, we can apply a rate of spread reduction factor. And we'll also look, so we do that using the label and just looking at the number of pixels in a patch. And for small patches, which are a different case, we check to see if they're within their size range. And then we will fill those areas with a rate of spread reduction. And this feeds back again and again so that we can actually exclude patches where they themselves have had a rate of spread reduction from influencing their neighbours. So yeah, it's a fairly complex kind of process. So what were some of the challenges that we faced? Debugging is a relatively difficult challenge because the data is so large. What we did to solve that is, in addition to going through and using separate tools to actually kind of theoretically examine different cases, we also found places in the vegetation by searching through them manually that would be good test cases for the algorithm. And then we sliced our input data to that area to actually visualize and just process that area. And one of the really interesting things about Dask and lazy processing is that often you can actually do that at the end of your processing chain, right? Because everything's lazy, you can set your full processing pipeline up and then you can just slice the end result, and if all's well, it'll just process that slice all the way back through your processing stack. But the algorithm that you've written is exactly the same as the algorithm you're going to implement for the full scale, and all you need to change is just what region you're asking for at the end. So we also did quite a bit of visualization. So you can see down here, this is some of our code where we actually dumped quite, like during development, we had code in place which would actually dump out to a passed in dictionary various steps in the image processing pipeline. So that algorithm was quite complex before, and there were bugs when it was initially implemented, quite a few, and it was necessary to kind of visualize each thing and think about it carefully. So we did things like output the patches with labels so that we could ensure that we hadn't, that we were identifying the right patches before we applied any rate of spread reductions to them. So some of the other challenges with the distance metrics, I think you can see that there are some artifacts there. We did have some issues as well, possibly because this is the first time it's the first time that I've really used map overlap. We had some issues with passing data structures into and out of map overlap. There was kind of an expectation that from map overlap that the data structures going in look like the data structures coming out. And in some cases, we solved that just by duplicating data structures on the way out of our algorithm and then just throwing one of them away effectively to conform to the shape expectations of map overlap and Dask. But it's also possible that there might be arguments or ways of setting up the function that I haven't discovered yet, or that we haven't discovered. So this work is likely to continue as part of a much broader project that's using Dask and X-ray and cloud platforms called the National Bushfire Intelligence Capability. There's lots of different kinds of processing going on, not just this proximity and size processing. We'd like to think about further generalizing this approach. So because we've been examining vegetation morphology, some of the discussions we've had are around whether or not we could apply this to house footprints, for example, and proximity, to habitat mapping in corridors, to water body extent and the isolation of water bodies from one another, and potentially produce some generalized vegetation layers. So rather than having them be produced transiently as part of a fire workflow, actually having them produced and delivers their own data entities that people can go and use as reference material to understand the nature of landscape. I think we'd like to look at approaches to work across tiles, and I think that Dask image may provide this. So from my reading, better debug and step visualization would be good. GPU approaches, of course, because a lot of these algorithms are well suited to GPUs, and Dask image, which I've already mentioned. So yeah, thanks very much. This work, apart from Kim and I working on it, there are others inside CSIRO who have been really helpful. So Alessio, Justin, Rob Woodcock, who is one of the primary, Rob Woodcock and Matt Padgett, who are primary drivers behind the Easy platform, which we used extensively, which was fantastic. Will Swedish and Paul Box. So thanks very much.
Thanks, Kim and Ben. That was a great talk. I really enjoyed that. There's quite a few questions popped up in the chat. So I would like to know which satellite data is used and if you have any notebooks or scripts made public.
Yeah. Yeah. Sorry. Kim can address what
satellite imagery. They're actually not at this. For this work, there wasn't satellite imagery used.
So the continuous vegetation was derived from
vegetation characterization maps that already exist. So that's that varying resolution and varying quality of data that we got. It was a large part of, it would have been a large part of the pie of work if we were to do that classification from satellite imagery. That is work that's going on in NBIC. And that actually, as a side, will be more valuable than what we're currently using, because currently we're translating ecological maps and characteristics to the attributes of the bushfire behaviour models. So basically we're wiping the deck and mapping attributes and making a bushfire behaviour vegetation classification map, which is quite unique.
And we have certainly more questions in the chat than I think we have time for right now, because we need to get to the next speaker. But I'll just ask one more, and then for the rest, we'll be able to move over into the Gather Town after our second talk for today, and give everybody an opportunity to go into more detail. But the most requested kind of information here is, what's the best chunk sizes with map overlap? And I know this is a tricky one because it depends so heavily on what kind of data and the context you're in, but maybe you would like to talk a bit about for you.
So to be honest, I don't have like handy what the exact chunk sizes we used are, but if you contact me via email, I can probably get those for you for our imagery. I can make a general comment that we have been trying various approaches with our data. So we've used TIFFs directly, and in some cases we've found that, so not cloud optimized GeoTIFFs, and in some cases we've found that the best chunking there is actually to read an entire row of pixels, or a couple of rows of pixels, so have chunking like 30,000 by 10 pixels. But in this case, we need to read enough for the map overlap process to work correctly. So we've also tried things like cloud optimized GeoTIFFs and ZAR as well, in various cases, not necessarily in the case that we've been talking about today. So we're really still exploring chunk size. Yeah, it does depend a bit on your cluster as well, I think, about how much memory you've got available, and processing, because you can kind of go quite large, but you want to use all of your CPU capacity if you can as well for this kind of task. So it's probably a variable amount. So I'm sorry if I can't get really good specifics there, but I don't think there's a number.
It does really depend not only on your data, but also the resources you have available. So we're going to get to all of these questions. If they don't get answered in the chat, don't worry, we'll get to them on GatherTown. But that is all the time we have questions right now, because we're going to move on. So thank you very much, Ben.
Okay, thanks a lot.